Let's try some elliptic construction moves. In this case, I'd like to make a couple of congruent elliptic triangles. There's several 10-point questions on the wiki that if you could just construct congruent elliptic triangles, you'd get your points. Well, there's lots of ways to make congruent elliptic triangles. Let's do an easy one. So notice I start with the crosshairs in honor of rifle season, and that just pick a point anywhere on one of these two crosshairs. I'm going to mark it there. I'm calling it C. C for center. And now I'm going to make an elliptic line. So I'm going to put the point of my compass at C. I'm going to adjust the pen to catch that antipodal point. And before I draw, making sure I'm catching that other antipodal point. Looks like I'm going to miss it by just a hair. Let me try that again. I'm a little bit closer to that end than I am to this end. So I just want to make it look good for you guys. There we go. That's going to do. So I've got an elliptic line. Now, I'd like to make any old angle I want. So check this out. I'm gonna go over here, and I'm gonna mark a segment, or sorry, a length from O to there and O to there. And now I'm going to draw those segments in. Now those two segments I know are the same size because they have the same size radius. There's an undrawn Euclidean circle there. These two segments are constructed to be the same size. They're the same Euclidean size, but they're also the same elliptic size because I'm measuring from O, the same distance out. So even though, yeah, the Euclidean distance formula isn't the same as the elliptic distance formula, when you measure from O, you don't have to worry about any distortion. Whatever amount of distortion happens here because of elliptic distance formula, it's the same amount that happens there. So I'm going to mark these points as A and B. And I know right now, here's what I know right now. I have elliptic isosceles triangle OAB. These two sides are the same size. It's an elliptic isosceles triangle because this orange side is on an elliptic line. Well, it's the case that these angles there are the same size as well because it's an isosceles triangle. Now I'm going to mark this point and call it D. And I know something really smart. That angle at D is 90 because the Euclidean center is on this line. That's a nice trick that holds in hyperbolic and in Euclidean. Do you see, Coco? It's a trick from hyperbolic that works in elliptic. When the center, oh, she's smelling the ink. Well, what do you think? When the center, that's C, is on that Euclidean radius, then you get that nice 90-degree angle. Well, I got a pair of 90s right there. And I've got this pair of angles the same size. This pair of sides the same size. But do we have angle, side in elliptic? No, we don't. But we can get something else that went unmarked. If you think about it, the construction marks that I did here make this D the angle bisector of these two. That's how you would make the angle bisector. Or there's a couple other ways to think about it. This line being perpendicular to there, it must cut this Euclidean arc in half. So these two sides have to be the same in Euclidean length. Well, that doesn't prove that they're the same size in hyperbolic length, but we might be able to build that case. But what we do get is, if I got an angle bisector, which I do, I mean, we built it to be an angle bisector, I've got angle for these two triangles here. So I get triangle OAD congruent to triangle OBD. Let's list why. Let's write down the because. Because, okay? OA congruent to OB by Euclidean radii, let's call it by equal Euclidean radii, centered, with an endpoint at O. So they're going to be the same size in elliptic. So I'm doing elliptic proof, but I'm giving a Euclidean reason. All right, so that gives me those two things, which implies triangle OAB is isosceles, which implies angle A is equal to angle B, base angles of isosceles triangle. So I've got those angles marked, and then we have the right angles. So I've got the right angles at D, OD perpendicular to AB, because center C is on OD, the extended line. So I've got those right angles, and if you look at the construction for OD is like the angle bisector construction. Angle AOB has OD as angle bisector. So angle DOA equals angle DOB. So we've got AAA for the congruent triangles. So that's how you can do congruent triangles. And if all you have to do is construct them, and you don't have to prove them congruent, well, a lot of things can help. A lot of basic instinctual things can help. I want to give you one idea that's really helpful for your the rest of your semester, these last 3 weeks when we're doing elliptic constructions. This should make sense to you. I've got circle O, and it's this gray circle. It's this pencil circle. Then I've marked out a distance OC1, OC2 to be the same Euclidean distance. So that's what this orange circle is, just to make sure that those two distances are the same size. Then I used C1 to be the Euclidean center for this elliptic line that goes through D2. I used C2 to be the Euclidean center for this line. And what I'd like to do is just be able to say, well, doesn't that make OD1 the same size as OD2? Well, it certainly does. But let's see the thinking behind it. Let's lay it down, the thinking behind it. So what we've got is we started with certainly the case that OC1 has to be equal to OC2 because they're radii of the same circle, radii of the big circle, the big orange circle. So those are the same size. Then I also happen to know that I can subtract this distance D1, D2 from both of those. So I'm going to minus the segment D1, D2 from both. And that's going to give me, if I take away this segment from both, C1, D1 is equal to C2, D2. And you can see where we're going from there. C1, D1 equals C2, D2. And then all I have to do is say, okay, now look, OC1 was the same size as OC2, the radii of the same circle. If I take away C1, D1 from OC1, I get OD1. Subtract those from the two given radii, the two radii we start with, from OC1, OC2, and we get OD1 equals OD2, which we knew. I mean, this is an obvious thing, but I want you all to be able to use this idea. If you ever, now look what we got. A very easy way to make, to be able to have these distances the same. You say, well, McDaniel, couldn't we start it out with, just mark this distance from O to D1 and O to D2 with the same size compass? Couldn't we just do that? And I said, well, yeah, but you don't have them on elliptic lines. Then you got to go and build elliptic lines that go through D1 and D2. Well, here I made elliptic lines of a convenient manner, and they gave me these distances the same without me building these two distances to be the same. I built the lines to give me those two distances the same. So let's see what we've got here. I've got, like, if these two sides are the same, well, this side is in common, and I've got right angles here and here, and I got right angles there. I've got congruent right triangles here, because I could say I have side angle side, because I have the central, these two angles are 90, I've got these two distances the same now, and they share a side. So side angle side gives me those two triangles the same. I got vertical angles. I could